Thank you. Thank you very much for the invitation. This is a very nice meeting. I've been really enjoying the videos and the notes, although as I was saying before, I really couldn't follow any of the talks live, but I still have the feeling I have followed the whole conference. So I will use some of the stuff that has been explained already, and hopefully I will manage to explain the ideas of the proofs also. So the the starting point of these, so I will present joint work with Ruben Martos, but most of what I'm saying is much older and much more general. Um, and the new results are on the archive written here. Now, the starting point of all of this has already been mentioned a couple of times during the conference, namely uh, the equivariant Kasparov category, which I'm going to write KKG, is not just a category; it's a tensor triangulated category. And in fact, well, it's true for a G any second countable locally compact group, and you can even take more general things here. But at some point, I will only look at finite groups anyway. So the point is that this tensor triangulated structure is what lets us do a lot of the things we want to do, all the homological algebra and much more. So I'm going to just revise quickly what this structure is, and I will only use this in the statements of the theorems, but near the end I will have to use some infinity category enhancements, and I will explain why. So a TT category needs to be, well, a symmetric monoidal category, in the usual sense, one category with a symmetric monoidal structure. And here the objects are separable G-C-star algebras, complex G-C-star algebras. The home sets, actually abelian groups, are the zeroth KK theory groups between the two algebras. Composition and the tensor product of maps, traditionally called the Kasparov product. And the tensor product of two objects is, well, I will choose the minimal tensor product equipped with a diagonal G action. Although I could have taken the maximal one for everything I'm going to say, nothing will change. But we also want to do homological algebra. So to do this in a minimal way, with a minimal effort way, maybe we can just remember what the triangles are. So in a triangulated category, you have this collection of diagrams. These arise from, well, equivalently from semi-split extensions. So extensions of sister algebras, G-sister algebras with like a G-equivariant, linear, continuous, completely positive splitting of the surjective map. But also more topologically, you can look at these as being the Puppe sequences in non-commutative geometry. Then, of course, we have the suspension functor, which is just the usual one in the sense of sister algebras. And both periodicity tells us that actually suspension and desuspension here is the same thing, because we can only translate twice and then we are back where we started. So sigma square is sigma. And all the gradings that come from the homological algebra are going to be Z-mod 2 gradings, as you well know. And then, of course, we want some compatibility between the triangulated structure and the tensor structure. But for us, it would be enough to ask that the tensor product is exact, which means it preserves distinguished triangles in each of the two variables. And that's essentially all we need. So that's nice, because TT categories is short for tensor triangulated categories, well, are a light axiomatization of stable symmetric monoidal infinity categories, so stable homotopy theories in some sense, and they are light enough that algebraists, representation theories and so on, are very happy to use them, even though maybe they have really no motivation to do topology, So it's really an algebraic theory. And so we are axiomatizing the homotopy category of these things in a light way. Now, one reason to look at this structure is that you can use it as the input for doing geometry. This is now quite an established theory, due mainly to Paul Balmer. So the idea of this geometric theory goes by the name of tensor triangular geometry, or TT geometry, is that just like if you have a commutative ring, you can define the Zariski spectrum of prime ideals, which adds some geometric way of thinking to commutative algebra. Well, if you have a commutative algebra in the stable homotopy sense, then you can also extract a geometry by a similar construction. And the construction is very similar. It's called a spectrum. Let me write SPC instead of spec, just to make sure that I'm looking at it now as just as a topological space. And for any essentially small TT category K, curly K, then its spectrum, it's some topological space defined as the set of proper tensor prime thick subcategories inside K with some kind of Zariski topology. But the actual definition is not so important, because then we want to identify it with something more concrete in each of the examples. So I'm not going to give you the definition in the abstract. But this space has very nice properties in general. So let me explain. Each of the objects A of this TT category K has a support, which is a subset, let's call it sup of A. It's a subset of the spectrum, which detects where the object lives, and outside of its support, it will be zero in some sense. Just like one thinks in when you do commutative algebra inside algebraic geometry, you think of modules, shifts of modules, and so on as living somewhere in their support. It's exactly the same way of thinking. In fact, the algebraic or geometric way of thinking is a special case of this. Now, this assignment, which takes an object and gives it its support, is compatible in the obvious way with all the algebraic operations you have in the TT category. So the tensor product of two objects goes to the intersection of the supports. The direct sum goes to the union. If you have a triangle, you have a nice relation that says the support of one object is always in the union of the supports of the other two, and the suspension functor doesn't change the support. Basically, that's it. These are some basic axioms you want the support function to satisfy. And you can have different support theories, but this one has a very nice property, which is this main theorem of Paul Balmer's from 2005, that says that suppose now that K is not just an essentially small TT category, but it's also rigid. So each of the objects has a tensor dual. It's not necessary, but I want to make the statements a bit more readable. So under this simplifying assumption, then there is always an inclusion-preserving bijection between the thick tensor ideal subcategories of K and some kind of subsets of the spectrum, which now are called Thomason subsets. So how does that work? Well, if you have a thick tensor ideal subcategory, by the way, that's just a subcategory C, a full subcategory, which is a triangulated subcategory, which is closed under retracts. Also, that's what thick means, really. And then it's a tensor ideal. So if you tensor anything in C with anything else, it gives an object in C. Now, each of these subcategories, you can send it to its support, which is just the union of the supports of all of its objects. And that's a subset of the spectrum, which has a specific property of being Thomason. What does it mean? Well, I put it here below. A subset S is Thomason if you can write it as a union of closed subsets, each of which has a quasi-compact open complement. And as you can maybe guess, the support of a single object is such a closed subset with a quasi-compact open. But you see that this bijection in the theorem doesn't really need to, it's not about objects, it's about thick subcategories and some kind of subsets of the spectrum. Now, this is very useful because, for example, in many contexts where you would like to classify the objects of your TT category, you cannot. There are actually theorems that say that there's no hope of achieving that. But this theorem still gives you a rough classification of the objects because, as I wrote here, two objects have the same support, really as subset of the spectrum. If and only if the thick tensor ideal generated by A is equal to the thick tensor ideal generated by B, because taking the thick tensor ideal generated by something is the map that goes backwards in the bijection. Sorry, it's not really that. But essentially, so if you have a subset, you can take all the objects supported inside that subset. That's how you get back. But you can easily deduce from the theorem this first equivalence. And then what this means, that A and B generate the same thick tensor ideal, is that you can build A out of B and B out of A by using all the operations you have in a TT category. So you're taking mapping cones, suspending, direct sums, retracts, and tensoring with arbitrary objects. So it's a very rough classification, right? But it's actually very useful because it exists. You can have it always in the abstract, thanks to this theorem. And also concretely, if you can identify this topological space in a more concrete way, right? So it's actually very useful. Now, to make this more interesting, let's see what kind of examples you have. Nowadays, many Balmer spectra have been computed for many different TT categories. I will give you the first examples that were known. All of these have been basically pre-proved in the 90s, I think, before the language existed for of the spectrum and so on. But they are, in essence, all the theorems. So the first example I want to give you is that if you have a X, which is a quasi-compact and quasi-separated scheme, for example, a Noetherian scheme or some algebraic variety in the classical sense, then, well, we can take the derived category of perfect complexes of OX sheaves. That's going to be a nice TT category with the derived tensor product of sheaves of OX modules. And Thomason, the same one who gave the name to these specific subsets of the spectrum, Thomason proved essentially that the Balmer spectrum of this TT category is just the underlying topological space of the scheme. And this is maybe not so surprising because so that's where all of these ideas come from algebraic geometry, essentially. So this example is very motivating. And look at the affine case. So if the spectrum X is the Zariski spectrum of a commutative ring R, then this translates as saying that the spectrum of perfect complexes, which is just simply the bounded homotopy category of complexes of finitely generated projectives, this is the Zariski spectrum of the ring R, right? So you can even make this more precise. You can recover also the structure sheaf and so on from the TT category, and you can actually embed algebraic geometry in this more general TT geometry via this procedure. So it's a generalization of algebraic geometry in some sense. But I'll give you other examples. If you don't care about algebraic geometry, maybe you only care about representation theory of groups, then you take G a finite group, K a field of characteristic dividing G, otherwise the next category is going to be 0. But otherwise, you can take the stable module category over the group algebra KG. So you kill off projective modules from the abelian category of all modules, and you get a triangulated category. And by results of Benson, Carson, and Ricard, then the Balmer spectrum of this TT category is the projective variety of the group. So the proj variety of the graded cohomology algebra of the group with coefficients in the field K, which has been used to, for example, to prove that certain KG modules are not isomorphic because they have different support and so on. So this theory was known before. It's another special case. Now, if you are a topologist, maybe you care about spectra. So let me talk about the third example. You can take the compact objects in the stable homotopy category, namely the homotopy category of finite spectra. And by the famous thick subcategory theorem of Devinat, Hopkins, and Smith, then you can describe the Balmer spectrum of this TT category too. And I'm not going to do it. Here's a picture. But for every prime number, you have an infinite tower going up to infinity plus a point at infinity. So this is the algebraic geometric picture. Each vertical line means the point above is a specialization of the point below. It's in the closure of the point below. So there is a generic point making this a connected space, and then you have over each prime you have an infinite tower. So this is kind of the spectrum of the integers, but blown up into infinite towers. And these are precisely a way of seeing the chromatic towers at all the primes p at the same time. So, all right. So what about KKG? It's a TT category, right? As I said in the first page. It's essentially small, right? We're only looking at separable GC star algebras. So what about his spectrum? Well, I must say that unfortunately, nobody has any idea, even for the trivial group G. Now, this is not because you know, I mean, there are very good reasons for this. It's not because there is something wrong with KKG, of course, but for the purposes of this theory, it's a very particular category. So let me try to tell you why it doesn't work. By the way, it would be nice to know the spectrum, the Balmer spectrum of KKG for a locally compact group G, because if you know it well enough, then I can tell you whether a very strong version of the bound-Kohn conjecture holds, namely when the gamma element for G is the identity, whether it exists. But I don't want to talk about that because it's going to be a bit complicated with lots of caveats. So let me just skip that. But just to tell you that there are reasons to look into these spaces. But there are many problems, and in fact, which make this uncomputable and so useless. Now, what are the problems? Well, first of all, KKG is not rigid. In fact, in general, you can find tensor nilpotent objects which will not have a tensor dual. So, well, it's not good. It's too big in some sense. In fact, it has too many objects, too many different objects. In fact, it has no sensible set of generators. And in all the examples I mentioned before, you do have a nice set of generators. Sometimes it's just the tensor unit object generates everything, like for the stable homotopy category. Sometimes you have a bigger set of generators, but they're always nice and you can tell stuff about them. Here, there are just too many different non-KKG equivalent sister algebras, even for the trivial group G. And then there's sorry?
One question. Do you have an example of a tensor nilpotent algebra?
Yes, in connection with the bound-Kohn conjecture. You take an object. So the thing is, there are tensor idempotent objects. And then if you take some cones of certain maps between these, then you get tensor nilpotent objects for. So how to say? You can look at. So I didn't want to talk about this, but other people have mentioned during this conference the point of view on the bound-Kohn conjecture introduced by Ralph Meyer and Richard Nest, right? And that you have this, the assembly map becomes a map from a certain object into C inside KKG, right? And so you can, in certain cases, you can look at the mapping cone of this map and conclude that it's tensor nilpotent. I think that's how you can have example. Maybe I'm wrong, but something very close to that. I was surprised at first when I saw this, but actually, it was there are examples. So if it's not exactly this, is something similar, which I don't have in mind right now.
Sure.
But
Thank
it's not surprising because if you have a big enough, so no, it's not exactly true what I want to say. Well, you probably know examples in the stable homotopy category, right? No? Well, there are examples there, but these spectra are not compact. They're not rigid. So in some sense, KKG is also too big, and in fact, it has infinite coproducts, and that's one reason why you can construct these tensor nilpotent objects. And to me, that's the main obstruction here to doing something reasonable. You have infinite coproducts. And whenever you have a category, even essentially small with infinite coproducts, a TT category like that, you're not gonna manage to classify the thick tensor ideals. So you cannot compute the Balmer spectrum because there are too many of them. And so it makes more sense. What you can try to do here, which is harder, but you can do it sometimes, is to classify the localizing tensor ideals, which means the full subcategories which are thick tensor ideals and which are also closed under the infinite coproducts, right? So I think at best you can hope to have that whenever you have infinite coproducts. All right, so why not do that? Now, I want to kind of solve all of these problems at the same time by looking at a certain part of KKG, which is nicer. And in some sense, it's the only part you can say structural things about with non-trivial statements. So what do we do? Well, we can try to classify the localizing tensor ideals in a reasonably generated TT subcategory of KKG. And I'm just gonna explain how to do that for G finite for simplicity. So many of the things I will say, like 80%, will be true also for compact Lie groups, at least. But it will make things a bit more complicated. So let's just do it for G finite. In any case, my results will be only for G finite. So what do we do to eliminate the above problems? Well, one choice of such a nice category is the G equivariant bootstrap category. So for G finite, this has many definitions. So for the trivial group, you have KK, and the bootstrap class, the classical bootstrap class of separable sister algebras of Rosenberg and Schochhet, it has many equivalent descriptions. And when you go into the equivariant setting, you can try to generalize any of them, and they might not coincide, they might not give the same class of G sister algebras. But for G finite, some of them actually agree. And so we have a nice notion of a G equivariant bootstrap category. So Ralph Meyer, and so in one article which I wrote with Heath Emerson and Ralph Meyer, we had this definition. You can take all the G sister algebras A, which are KKG equivalent to a type 1 sister algebra. And then you take the full subcategory. It turns out to be a nice TT subcategory closed under infinite coproducts, the countable infinite coproducts that you have. And in fact, you can prove that, well, basically Rosenberg and Schochhet had almost already proved this, that for compact groups even, that this has a nice set of generators. It is the localizing subcategory generated by algebras of this form. So they are induced from some subgroup H of G. And what do you induce? Well, some action of H on some Mn of C, some n times n matrix algebra, and then you induce them up, and you get a set of generators. But actually, now we know that because of results by Arano and Kubota, which I learned from a paper of Ralph Meyer and George Nadarashvili. And by the way, this I think George already talked about this yesterday, right? So you can show even something much stronger, that it's enough to induce up from the trivial sister algebra for each of the subgroups, and in fact it's enough to take cyclic subgroups. So that's quite I think a strong result. It's enough to take these objects here to generate this bigger bootstrap class. So we're going to use this result that this orbit function algebras with induced G action, they suffice. So only cyclic subgroups need to be taken to have a nice set of generators. So this equivariant bootstrap category, boot G, it's a much nicer TT category. It still has countable infinite coproducts, but it is generated by a NAS set. Its compact objects and its dualizable objects coincide. This is a technical hypothesis which is used most of the time in TT geometry. So what does this mean? So the class of compact objects in there is that of those objects that when you map out of, it commutes with coproducts. So you send a countable coproduct of a countable direct sum of GCSR algebras into a countable direct sum of the abelian home groups. And on the other hand, you could look at objects which are dualizable for the tensor product, for which there is a right adjoint another object, so that tensoring with A is the same as tensoring with the dual on the other side of the home. So a priori they have nothing to do with each other, but they agree inside boot G, which is very nice. In particular, these two categories agree, and they are therefore a TT category, a TT subcategory, because the dualizable objects are always a rigid symmetric monoidal subcategory, and the compact objects are always a triangulated subcategory, and then you put the two together, you have a tensor triangulated subcategory. And it is essentially small because this category is actually the thick subcategory generated by the generators. And there are finitely many of them, and then, well, you get something essentially small. Very nice. And then you have something else. So if you any of these compact slash rigid objects has a finitely generated K-theory groups as modules over the representation ring R of G, and that for all subgroups. I think you should be able to prove the inverse implication, but I'm not exactly sure of all the details. I think it's true, but I'm not sure how to go about it. So these are nice objects, okay? And they form a nice, essentially small TT category. So maybe we want to compute the spectrum of that. All right. So what we can do is that with Ruben, we can prove that for some class of finite groups, we can actually classify the thick tensor ideals of the compact slash rigid objects. So which means we can compute the Balmer spectrum of that TT category. And we can also classify the localizing tensor ideals of the bigger one, of the whole G-equivariant bootstrap category. And I will say how. So let me first tell you for which finite groups this works. So unfortunately, we cannot prove it for all finite groups yet, but at least for, at least for finite groups G of prime order elements, by which I mean those for which every non-trivial element of the group has prime order. Now you might think, okay, that's a very restrictive hypothesis. Yes. But, well, of course you have the cyclic groups of prime order, but you have finite products of these if the prime is the same every time. You have S3, you have A5, you have all finite P groups of exponent P. You have, of which there are non-abelian ones, as long as P is not 2. So you can actually have many non-obvious, non-abelian groups which fall into this class. And they're all covered by this theorem. Now, the reason why I require this is that we want all the non-trivial cyclic subgroups to have prime order. And I will tell you exactly why. So what are the results that we got? This is kind of the state of the art for now. Is that if G is such a finite group, then we have a canonical homeomorphism between the spectrum of the compact objects in the bootstrap class, so the Balmer spectrum of this essentially small TT category, and the Zariski spectrum of the complex representation ring of the finite group G. So this is a well-known space. It's been well studied by Graham Siegel, for example. So this is a very nice thing to have. Now, if we have these, then we can also prove something else, namely, first of all, if G is any finite group, then we can extend the Balmer support theory, which a priori, takes place in the spectrum of compact objects, so only works for compact objects, but we can extend it nicely to arbitrary objects in the bootstrap class. So it gives a function from all the objects into subsets, which are not necessarily closed now. There are some subsets of the spectrum of the compact objects. And then if G has this prime order elements property, we can show that this is actually a bijection. It induces a bijection between the localizing tensor ideal subcategories of the G equivariant bootstrap class and arbitrary subsets of the Zariski spectrum of the representation ring. So this is what is usually called stratification when you have this kind of bijection with the localizing tensor ideals. So I hope I'll have time to explain stratification. So first of all, let me tell you that we fully expect both theorems to hold for all finite groups. And in fact, this result by Arano Kubota plus general stratification theory lets us reduce both theorems to the case of finite cyclic groups, but finite cyclic of arbitrary order, not just prime. It just happens that the case of a prime order was treated basically in a previous work joint with Ralph Meyer. So we knew how to prove theorem A, this one, in the case G is finite of prime order, and it's not super hard to also prove theorem B in that case. Now, how I want to explain to you how the proof of these two goes, and at the same time I will tell you that there is this big machinery called stratification theory, which you might think it's also maybe useful for other in other settings or for other things. But before I explain that, let me repeat. So here we have obtained a rough classification of the tensor dualizable objects in the G equivariant bootstrap class in terms of Thomason subsets of this Zariski spectrum. And Thomason subsets here are just specialization closed subsets. Those subsets which are closed under taking specializations of points in the sense of algebraic geometry, in the sense of points containing the closure of a point which is in there. So these are quite easy to describe, these subsets. And in theorem B, we have that arbitrary subsets of this same space classify general localizing tensor ideals, so big thick tensor subcategories closed under arbitrary countable coproducts in the equivariant bootstrap class. So there are two classifications, very concrete, because each time I can tell you what the support does in terms of, for example, equivariant K theory. Now, all right. As I was saying, the case of G cyclic of any order n, and therefore the general case of finite groups G remains unproven, but the analog statement, and maybe I will tell you what it is, in equivariant topology is proved. And there is a reason to think that, in fact, they are kind of the same statement, because there should be some kind of equivalence of categories or something very close to that, which allows us to conclude also for the equivariant bootstrap class. But not all details have been worked out of that. And this is something that I don't know how secret this is, but some people in the audience are working on. So let me tell you ideas for the proofs of these two theorems. Now for theorem A, that's the easier one. Well, first of all, this homeomorphism in the statement is actually given by a map which always exists. There is a natural, continuous, very nice map from the Balmer spectrum of any essentially small TT category K into the Zariski spectrum of the endomorphism ring of its tensor unit object. So this is the tensor unit object. So as in any monoidal category, its endomorphism ring is a abelian. It's commutative, so it has a Zariski spectrum, and this map is a very explicit map you can write down in one line if you know the definitions. And in general, it's neither injective nor surjective, okay? There are many examples. In each of the examples, 1 and 2, it's rarely a bijection, but sometimes it is, and here it happens to be. Now, using general tensor triangular geometry and the reduction to cyclic subgroups afforded by Arano-Kubota, and the structure of the Zariski spectrum of the representation ring, as explained by Siegel in the 60s, we can reduce to the case of cyclic groups, but because of the extra assumption on G, in fact, all cyclic groups are either trivial or prime order. The trivial case is kind of easy, and that's just looking at the classical bootstrap class, and it's kind of easy to see what happens there. I think I did it during my thesis. And then the case of a P prime, this is what we did with Ralph Meyer a few years ago, and this uses Köhler's universal coefficient theorem that was mentioned by George yesterday, I think. It's a very useful computational tool in this specific category, in the bootstrap category for Z-mod PZ. So I'm not going to go into details, but this is the strategy of the proof. And as soon as we can do the case of a general finite cyclic group, we have all finite groups. Now, what about theorem B? Well, this is what actually needs a lot of stuff, even enhancements. So first of all, we want to use stratification theory because this is the theory that has been developed since the 90s for classifying localizing subcategories in big triangulated categories. Now, this is actually one of the, some of these results go way back to work of Hovey, Palmieri, and Strickland. And these are topologists who used TT categories as some axiomatic stable homotopy theory, and they redid a lot of topology in there in bigger generality, and they had this idea of stratification. Although it didn't work in topology, it cannot work in the stable homotopy category, now we know. But it does work in similar categories like the derived category of a commutative Noetherian ring. This was results by Niemann. Then other people, Benson, Jenger, Henning Krause, have developed a more abstract theory. And then lately, Bartel, Ruherd, Ben and Sanders, they have, so again, topologists, they have really established this as a powerful theory that can be applied almost as a black box in many contexts. And this is what we want to do. So the setting is the following. Now, we have our TT category K, okay? It's essentially small, it's rigid, so every object is tensor dualizable. But actually, it lives inside a big TT category with arbitrary coproducts, let's call it T, as the subcategory of compact and dualizable objects, which must coincide. So this is the setting. And this big category, it's something called now a rigidly compactly generated TT category, or if you are Hovey, Palmieri, Strickland, you call it an algebraic stable homotopy category, or it has many names. What it means is that it has arbitrary coproducts, but it is generated by compact objects, by a set of compact objects, which are also dualizable. And well, that's essentially it. So, for example, if you take C to be a presentably symmetric monoidal stable infinity category, which happens to be generated by a set of compact and dualizable objects, then its homotopy category will be one of these nice big TT categories, T. Okay? So you have many examples from abstract modern topology. Now, we need to suppose something else for this theory to work. We need to suppose that the Balmer spectrum of the rigid and compact objects, which I call the K, this TT subcategory, should be Noetherian as a space, or at least weakly Noetherian, but let's not go into that. So what this means is that every open subset is quasi-compact. For example, take a commutative ring R, take the Zariski spectrum. If the ring is Noetherian, like the representation ring of a compact group or finite group, then the Zariski spectrum is going to be a Noetherian space. Okay, so this is an example that covers our case because we know from Siegel that the representation ring is a Noetherian ring. All right, so under this hypothesis, these two hypotheses, the structural hypothesis on K, that belongs to this bigger, nice category, and on the spectrum, which is Noetherian, then you can do lots of things. The first thing you can do is to extend the support theory to all objects, not just the compact ones. Now, this has been done by Balmer and Favi in 2011, and it works nicely under the above hypothesis. And it also induces always a surjective map that goes from the localizing tensor ideals of the big category T into arbitrary subsets of the spectrum of the compact objects by assigning the localizing subcategory L to the union of the supports of all the objects, which is some subset. And the question is, well, we want to know whether this is bijective. So when is it also injective? And this is where the results come in. Now, Bartel, Hurd, and Sanders have the best results so far about this. They say that the map is also injective and therefore bijective, and so it gives a classification of the localizing tensor ideals. And then one says usually that T is stratified, if this holds, provided that for every point of the Balmer spectrum, a certain localizing subcategory, localizing tensor ideal, actually, I should say, or in fact, that of the objects supported only at that point P has to be minimal. So it has to be non-zero, but that's okay, always the case here. And it cannot contain anything else, meaning any object in here needs to generate the whole LP. So I don't want to go into details, but if you have minimality of all of these categories, then it's the same as having injectivity of the map. It's kind of intuitive, but uses a lot of stuff. And the advantage here is that this minimality can be checked locally with respect to the spectrum. So you can simplify your TT category T and K by localizing, by taking like étale covers, all sorts of techniques to divide and conquer. And so for each point, maybe you have a different technique, which allows you to tell you that this category is minimal. And if you can do it for all the points, then you have one, right? And this is what we do. So for a crucial case of the bootstrap category for a cyclic group of prime order, we can actually do it by hand, point by point. There are two kinds of points. We look at them, see what happens, because the spectrum is just, as we already know, it's a polynomial ring with integer coefficients modulo x to the p minus 1. Take its Zariski spectrum. We have a complete description. We know what happens. We can even apply Köhler's UCT if you want to compute everything explicitly, and it can be done. That's the idea, right? And again, by Arano and Kubota, if we could do it for every finite cyclic group of any order, then we could have it for every group G, because certification also, because of this local property, you can reduce to subgroups in some way. I'm not going to explain how, because it's complicated, but it's a machinery that works well for this. Now, there is a big problem, though. It's that this stratification theory actually only applies when the TT category T has arbitrary small coproducts, not only countable infinite coproducts. And if you remember, the bootstrap category of separable G-sister algebras, well, inside KKG, the coproducts are, direct sums of G-sister algebras. Well, we only have the countable ones. So you cannot apply the theory directly. You have to say something. So you can spend a few months trying to reprove the theory in the countable case, but it will not work because there are things that do not work if you only have countable coproducts. So you have to adapt the theory and see what doesn't work, and you go a bit crazy. And I've tried to do that, and it's very frustrating. So a better way of solving this problem, actually, I learned it from Uli, from a paper by Bunke, Engel, and Land, where they actually provide in a very straightforward way, in some sense, an infinity categorical enhancement of KKG. And then they can make it bigger so that it contains all arbitrary coproducts or homotopic limits, if you want, not just the countable ones. But it's done nicely. It's functorial in G. It contains the original KKG, respecting all the structure. And so that's what we want to do here, so that we have a bigger setting where we can apply the abstract stratification theory and then try to deduce the results for the original KKG. So this is how it works. So by the way, the bootstrap category is rigidly completely generated in some countable sense. It is nice. But the fact that you cannot do all the constructions, but only the countable ones, is really a handicap for many things. For example, this extension of the Balmer-Favi, so the Balmer-Favi support theory for big objects works in the same way. That's one of the easy things, right? It's part of the theorem B. But some things don't work. So the solution is this. Well, we can take any enhancement, KKG, let's say infinite, which is going to be some, symmetric monoidal stable infinity category. So the homotopy category is going to be a TT category, a tensor triangulated category. And we want, which I forgot to write, we want that this is, as a TT category, is the same as a KKG, right? The one we already have. Okay, we can do it. I think we saw a construction in detail in the case where G is the trivial group. It works in the same way even for at least discrete countable groups and probably all locally compared groups. A bit more complicated maybe. And then what do you do? Well, and then you use the infinity categorical machinery of Lurie and others to just adjoin all small homotopic limits. And you can do this in an easy way. So you do the in the construction. But we're going to do the in construction relative to omega 1. So we are going to, in fact, universally add arbitrary homotopic limits, but in a way which preserves the countable homotopic limits we already had. This is important for us because then when we take the homotopic category, we get a TT category T, which has arbitrary coproducts. But if I look at the countable coproduct in here, I want the resulting enlargement, embedding, to preserve them. So the countable coproducts here have to stay coproducts in here. And if I just do the normal in the object construction here for infinity categories, that's not going to work. I will forget all kinds of infinite colimits I have here and create new free ones. So I want to preserve the omega 1 small ones, so the countable ones. Okay, that's a variation on the construction explained by Uli in his talk, I think last week. So this can be done. It's kind of you can do it in many ways. It doesn't matter which, as long as you get some nice TT category T, which is rigidly compactly generated as I need. And then its compact rigid objects will have to be the same as in here. Okay, maybe I should say it. And if you look at the compact or dualizable objects will have to be the same as in here. And this is not so hard, because once you have this for, so how to say, you just pick the same generators here on the right-hand side as you have here, and then look at the localizing subcategory generated by that, and it's going to work. And then the compacts are the same, more or less, by construction. All right. Now, there is some stuff to be done as to ensure that that the generators are compact here, but it's kind of, it follows also from the machinery. If you cite enough lemmas from Lurie's books, it's kind of straightforward. Then
Yes, a question from the chat, namely, is minimality of the localization equivalent to the fixed subcategory of acyclics being generated by the compact operators?
acyclics for what? In which sense?
Mm.
Cyclic subgroups.
I mean, the person asking the question writes acyclic. It would be maybe, I mean, I'm also not quite certain. It would be best if you could clarify.
Yes, I'm not sure I understand the question, sorry. Do I see the chat? Yeah. What is K in this question? Sorry, the category, the general category. No, it's not the same. No. Okay, if I understand the question, so it's not the. Oh, maybe it is. I don't think it's a trivial result, even if it is. Well, there is something called the telescope conjecture. So maybe it is true. So if you have a, so I think that the question is the following. Okay, I see. Yes, maybe yes. So if you have stratification, in many cases you also have the telescope conjecture, which, among other things, so what it says is that any localizing subcategory, which is smashing, whatever that means, is generated by computer objects. But if you have stratification, all of these things will have to coincide. I think you need something more, but if the spectrum is Noetherian, it's going to be automatic. So it might be the case that so now I'm a bit confused exactly by. So it might be true. It's not equivalent in general. I'm pretty sure that having certification means all localizing subcategories are generated by the computer objects they contain, but that would be the telescope conjecture, essentially. But it's very close to being the same thing. Is that okay? So for the details, you will have to read this article by Bartel, Hurd, and Sanders, published in 2023, where they explain everything. There are some little hypotheses that have to be put. For example, if the Balmer spectrum is not Noetherian, but only weakly Noetherian, the theory still works, but some results don't. So there are some things to be said. So let me just conclude the thought here. So now we have this bigger TT category here, which is one of these rigidly completely generated TT categories for which people know how to do stratification theory. So we apply stratification theory, as I said, almost as a black box. We just apply the many powerful results they have, and we obtain our stratification, not of the usual bootstrap category, but some bigger version which has, arbitrary coproducts. So, okay, but surely if you have stratification in the bigger guy, you can deduce stratification for the slightly smaller one, right? And it is true. It's something you can prove at the purely tensor triangular level. No need of enhancements for that, but it is its own result. So it's kind of not completely trivial. It uses results from the theory of well-generated triangulated categories, which are non-obvious, but it's a general effect. So basically, we have a stratification in T, and we then deduce that, the localizing subcategories in here, those closed under countable coproducts, are classified by the same set, namely arbitrary subsets of the Balmer spectrum of the compacts, which by construction are going to be the same, right? So this can be checked, and then we conclude and we get theorem B. All right? Okay, so that's what I wanted to explain. So I will stop here.
Let's all thank our speaker. Are there questions? Yes, Uli?
Yeah, so I mean, if you want to check the stratification thing, so I mean, so what do you use really? I mean, as far as I understood, you check this local condition at every
Yeah.
point, yeah. But so I mean, in principle, I mean, do you use anything about KK here, or is it? I mean, what
Yes,
is
yes,
the
yes.
input?
I use something about KK. For example, the case of the trivial group also has to be handled for this to work. And what do you do in the case of the trivial group? You have the classical bootstrap category. It's generated by its tensor unit, because now you only have one generator in this case. Is the complex functions on G mod G. That's a trivial group. There are no other subgroups. So for these TT categories, you have kind of something a bit formal that goes on, but you still need to know the properties of the bootstrap class and so on. So you can, of course, you can either cite the classical results from the 80s, or you can just redo everything in a more formal context and say, oh, when do I have the UCT and this and that? But you have to use the UCT, right? And the Kuhn theorem and so on. And then at some point you have to argue. You have to say, okay, it's essentially the same argument as you would do in the derived category of abelian groups. Why do you have stratification there, right? You have to do something. It's not completely obvious, but it's kind of known how it works. So I don't know how much that is C-star algebraic or KK theoretic, but
Okay, so UCT is the keyword. So this is,
yes, exactly.
I see the point. You can calculate the mapping spaces. Yeah, okay.
Yeah, and that's also why we can do the case of a cyclic group of prime order, because there is a UCT that allows you to actually calculate and say something about this category. If you had something similar for arbitrary finite cyclic groups, maybe we could also conclude in general, but we.
So a UCT spectral sequence, or I mean a universal coefficient spectral sequence wouldn't be enough for these solutions.
Depends. No, it wouldn't be enough. I mean, I looked at all the spectral sequences I could think of, and nope. What happens? Maybe you know the case of in topology. So this is something that I wanted to mention, but I haven't written down. In topology, you can look at modules over KUG, right? That's some TT category, which is nice, big but nice, rigidly completely generated. It is very similar to the G-equivariant bootstrap class, and some versions of both could even be equivalent. But how do topologists have proved stratification and the analog of theorem A for that category? How do they do it? They use something that we don't have here. They use fixed points, so the geometric fixed points functors, which you take your KUG module, you remember it's a spectrum with a certain action, and you take fixed points for subgroups. You land into the usual stable category or spectra, and these things have been computed. Like these geometric fixed points have been computed for some groups, in particular for finite cyclic groups. There are computations that allow you to say things, and these breaks down. I don't know how to redo this kind of computations in KK theory. It's not available. The analog, if I try to construct the analog of the geometric fixed point functors for subgroups, they don't even land in the right category. So, I don't know. There's something missing on the computational side in KK theory. Does it answer your question?
Okay, I think next is George.
Hi, Ivo. Thanks for the great
Hey,
talk.
hi.
So yeah, my question was basically answered right now, but just to reiterate, so in theorem A, you mentioned that so the missing link is basically on this side. The cake, it's the UCT for finite cyclic groups, right? Even square-free things would work, as I understand, right? In the proof, you said the idea that you use
Yes, square free is not the same as
like you have something for
elemented prime order,
squares
but
already, right? So z mod p to the power n or something you
okay,
resolve. Yeah. So the missing link is really the UCT for some cyclic groups that might be also square free, meaning.
Well, it doesn't have to be the UCT. There is something missing. Here we happen to have the UCT in these cases for the trivial group and for finite groups of cyclic groups of prime order, and so we use it to say whatever you want. But it could be something else. In topology, the analog statements use some computations with geometric fixed points, which are not linked directly with any UCT that I.
Yeah, that's very interesting. Yeah.
But so there is something missing on the computational side.
Yeah.
For arbitrary finite cyclic groups.
Mm-hmm.
If you have anything, if you have a UCT for general, of course, if you rationalize, maybe I should have said it because in your talk, you mentioned if you invert the order of the group, right, in your category, things simplify. So if you invert the order of the group because of your results, for example, if you rationalize the category, you get you can do all the computations, and then we can prove actually that we have stratification, and then the spectrum, the Balmer spectrum of the compacts is the Zariski spectrum of the rationalized representation ring. All of this it becomes easy, and you can prove it. But the rationalized category is actually a semi-simple abelian category. Mm-hmm. In this case, it's not. I mean, the geometric content is. I mean, the spectrum is a bunch. It's finitely many points. It's a discrete finite space. So, you lose a bit the geometry here.
Okay. I also had another question, but let the others ask first, maybe.
Okay, I think next is Valerio.
Ciao, Ivo. Great talk. Enjoyed it. So
Thanks.
I think you might have answered maybe this during the first answer you gave, but so for G trivial, right? So the dualizable subcategory of bootstrap is equivalent to like perfect KU modules, I think, or something like this.
Yeah, right. In the case of a trivial group, they are equivalent. Equivalent. The bigger version that I explained at the end, how to construct with enhancements, is going to be equivalent. Yes.
And the problem is that for a finite group, actually, you don't know whether this is true, because if it was true, then I suppose you could use the result from algebraic topology to get the.
Yeah, exactly. So I think now. So I don't know. I think I can say Benjamin here and Uli, they have a statement which is an equivalence of tensor triangulated categories, even at the level of infinity categories, between some version of the equivariant bootstrap category and some version of KUG modules. And I looked at that, and the only remaining question is, are these versions equivalent to the ones I talked about here, or just very similar? And if they are very similar, can you still conclude, So my doubt, which might, imply that they are not equivalent on either side, are the following. KUG may have different meanings for different people,
Okay.
And yeah, of course, the coefficient rings are the same and so on and so forth, but, So if you look at modules, a priori is a different entity category. That's not too big of a problem in some sense. But on the other side, well, when you construct this bigger version of KK theory and therefore of the bootstrap of the equivariant bootstrap class, you have to do it in a way which preserves the coproducts you already have, the countable ones. Okay, it can be done, but it's not exactly what, for example, Uli talked about in his first talk. So it's a variant, but as soon as you have a variant, then some of the things might be a bit different, and there is something to be checked, It's not, but you are right. If you can identify, the situations are very similar, very close, and I would like to know if you can really conclude that you have an equivalence between the things that people already studied,
Sure.
or something close enough to an equivalence. Yeah.
Okay.
I think at some point the answer will be yes, but and so everything I talked about now, or the results with Ruben Martus, will be kind of redundant, because if you have an equivalence, then you don't have to redo the certification here if you have it there, right? So what we did is just try to prove things in a different context. It might turn out to be the same things or not. I don't know.
Thanks.
Okay, we'll take one more question before we stop the recording. Jonathan?
Hi, thanks. Really nice talk. Very useful.
Thank you.
I was just wondering if you had thought about whether theorems A and B might be true for compact Lie groups, especially for ones, say, in the Hodgkin classes where pi 1 is torsion
Yes.
free, where the homological algebra of R of G is actually quite nice. So
Yes.
the sort of key test case really is G equal to the circle, right?
Yes. Very nice question. So I think the answer should be yes. Again, because topologists, in some sense, know how to do these things already. They have bigger and more oiled machines to unleash on their problems than KK theorists for these kind of things. But there's some stuff to be checked. So I don't know. I cannot affirm that all of this is true. But for example, it is true that everything I said about the representation ring is true. It's Noetherian, blah, blah, blah. It's nice. The problem is now that Arano Kubota, this that says that looking at cyclic subgroups for generators is enough. It's also true. So almost everything is true. So what remains to be done? Well, first of all, the case of cyclic groups, finite cyclic groups, still open as far as I know. So let's suppose we have this. Then you still need to do the reduction for stratification for theorem B, for example. For theorem A, it might be a bit easier. I think by looking at the results of Siegel on the structure of the Zariski spectrum of the representation ring for a compact group, I think theorem A should follow from the case of cyclic groups by similar arguments. For stratification for theorem B, I'm not so sure, because there is something about the topology, because how you put cyclic groups inside your, for example, the circle, right? So I'm not completely sure. I mean, there are some parts of the argument that needs to be adapted, and I haven't tried to do them. But it's certainly something nice, and I would like to see it done at some point. It will be interesting. I think it can be done. Yeah.
Okay, we'll stop the recording.